let me do a brief introduction. And our next speaker is Yashi Tiwari. She's a PhD student studying at the Joint Astronomy Program at the Indian Institute of Science, Bangalore, India. And she's interested in understanding and addressing some tensions and anomalies in standard cosmology by working in the framework of generalized scalar-tensor theories of gravity. She will be presenting her work on an Horndeski gravity model titled Towards a Possible Solution to the Hubble Tension with Horndeski Gravity. The stage is yours, Yashi.
Okay, thank you. So thank you, first of all, the organizers of the Journal Club to giving me this opportunity to present my work. So I am Yashi. I'll today be talking about my work, which recently got published, and I'll try to address Hubble tension within the framework of Horndeski gravity. I'll explain these terms as we go along in the talk. So the outline is as follows. First, I will talk about what is the standard model of cosmology, and then, but there are some issues. Particularly, I would be talking about the Hubble tension and what are the directions to the resolution of this tension. And then I will talk about, are there any hints of dynamical dark energy models which could resolve this tension? And this will motivate me to introduce my work, which is building a dark energy model in Horndeski gravity. And I will use the observations to put constraints on the model and then conclude. So starting with the slide, so we know that the present understanding of the universe is something like it started with a cosmological inflation, followed by standard radiation and matter domination epoch. And then at around the redshift of 1100, the photons and baryons decoupled from each other, and we first saw the cosmic microwave background. Then there were dark ages, formation of first stars, and the formation of large-scale structures that we observe today. And presently, we are living in a universe which is undergoing accelerated expansion, governed by dark energy. And all these picture is very nicely explained by the standard lambda cold dark matter model, where lambda stands for cosmological constant. And this model is based on cosmological principle of homogeneity and isotropy, along with the general theory of relativity. And this gives us the Friedmann equation, which tells us how the expansion of the universe could be related to the energy budget of the universe. And at present, this energy budget is, as already discussed by Marcin. So it's around 68% dark matter, 68% dark energy, which is mimicked by a cosmological constant lambda. And then there is dark matter around 27%, the ordinary matter around 5%, and a little bit of radiation. So then, but still there are some tensions in the standard model of cosmology, one crucial being the Hubble tension, which is the discrepancy in the measurement of the expansion rate at present, which is referred to as H0, from two different observations. One being the cosmic microwave background, which we refer to as early observations, and other being the inferred from the distance ladder techniques using CFIDs or supernovae, which are the late observations or even referred to as direct measurements. So here in the right-hand side figure, you can see that the top data points are from the indirect measurements from CMB, which prefer a smaller value of Hubble constant around 67, 68, whereas the indirect measurements from CFIDs, TRGB, and others prefer a value which is around 72 or something. And this left-hand side plot shows the evolution of the tension with time, that how it has emerged with passing years. And at present, it has become statistically significant up to 5 sigma, and thereby a crucial problem to look at. So before going to the Hubble tension, first I will discuss about how H0 is actually inferred from the early universe. So what we are observing is the CMB sky and the anisotropies in the CMB sky, which are of the order of microkelvin. And this is encoded in terms of the power spectrum, which is measured by Planck, which is a measure of 2-point correlation of these fluctuations as a function of angular scales. So here on the right-hand side figure, the red data points are the points from the observations of Planck, and the blue is the ΛCDM model fit to this data. And we say that the 6-parameter ΛCDM model, the parameters mentioned here in the table, actually provide a very nice fit to the CMB data. And H0 is a derived parameter in the theory whose value is around 67.3 kilometer per second per megaparsec. Now comes how this H0 is actually measured from the CMB observations. Just a quick introduction to that. So it is actually measured from this calculation where theta is the angular size of the sound horizon at the last scattering surface. And this is a cosmological parameter which is very precisely measured by the observations of CMB. And this is defined as a ratio of the co-moving sound horizon at the last scattering surface to the co-moving distance to the last scattering surface from present. The crucial point here to note is that theta is fixed by the data. Now RS, the numerator, is something which involves the pre-recombination physics, because it is the distance traveled by the sound horizon from the Big Bang till recombination. And whereas the D, the calculation of the co-moving distance to the last scattering surface, requires a late universe physics, where the particularly dark energy model of the universe will enter into the picture. And here is where the H0 information is contained in. So for a simple lambda CDM setup, where you just have lambda as the dark energy and the cold dark matter as the dominant components, it could be just written as H0 into Ez, and from here you can extract H0. Now, talking about the other case is the distance ladder techniques. These are based on some astrophysics of stars, like observing some standard candles in the local universe, supernovae or Cepheid stars, and calibrating the distance to them, and then using those to even calibrate the distance to further galaxies in the Hubble flow, say up to redshift of 0.1. Explained about the Hubble tension. Now, what are the possible resolutions? So if assuming that the local measurements are fine, then there is required a modification in the standard lambda CDM picture. Why? Because when inferring H0 from the CMB, we take this information that the model of the universe is lambda CDM model. So there may be something wrong in that assumption, or maybe some modifications required. And this divides the solutions into two regimes, the early universe solutions and the late universe solutions. The early universe solutions are actually trying to reduce the sound horizon. So the idea is that this theta is the ratio which is fixed by CMB. Now, if you want to modify the early universe, you have to decrease the RS, because if you say that the late universe is still well explained by lambda CDM model, so to increase H0, it requires reduction in RS. Similarly, if you want to modify the late universe, then it demands the modification in the denominator such that you change the expansion history such that this integral, the co-moving distance to the last scattering surface, is actually not disturbed, in order not to disturb the position of the peaks of the CMB. So this is the late universe solution. So I am not talking about the early universe solutions today. Those who are interested can look at these articles which tell that early universe solution alone cannot resolve the Hubble tension. What I'm interested in today is about the late universe solutions. So these are based on modifying the expansion history post recombination such that this D, which is the co-moving distance to the last scattering surface, remains undisturbed. So if you want to go beyond the simplest lambda CDM model, one simplest modification could be that you go for an equation of state which is other than -1. You go for a dynamical dark energy kind of model, and for such cases, the Hubble expansion could be written as follows, where W is now not equal to -1, it could be something else. And one can easily see that if you want to increase H0 and not disturb this integral, it would require you to go to a phantom regime where 1 plus W should be less than 0. And this is how phantom dark energy models are motivated. But in the simplest phantom dark energy models, there are problems because these worsen the sigma 8 tension, which is another crucial cosmological tension related to the growth of structures. So whatever models are proposed, sometimes they resolve one tension and worsen the other tension. So there is a need for some non-trivial dynamical dark energy model because simple models are not working. And we need to come with a model which tries to solve all the tensions simultaneously. Now, regarding dynamical dark energy models, we need some non-trivial evolution in the equation of state as a function of redshift. So what else information do we have? So I will point out to this recent work by Heisenberg et al., where they tell that what type of phenomenology the late dark energy models should exhibit in order to simultaneously alleviate the H0 and the sigma 8 tension. And this comes down to having a phantom divide behavior or the phantom crossing behavior in the dark energy equation of state. It means there should be a crossing in equation of state from a non-phantom to a phantom regime. I am trying to introduce a dynamics which could give rise to a phantom divide behavior, and I want to work with a model which has negative dark energy at high redshifts. And I'm looking for what is the motivation. Are there any signatures from the data that suggest that, okay, dark energy could be negative at high redshifts? So this brings to talk about the BO laminal phenomenon, which is the lamin alpha measurement of the BO signal at redshifts of around 2.34. And these data points, these are two data points, auto and cross correlation data points. These are actually not addressed by the simplest lambda CDM model, and they are at a tension of around 2 sigma, not very significant, but still they are considered to be the outliers. And there have been studies which model for example, I'm just pointing out here two works. There are others as well. So like for the first one, they talk about some model independent reconstruction of the profile of the equation of state of the dark energy, which should be there in order to address these Lyman alpha points. And the other one is the paper by the Boss collaboration itself, where they explored the possibilities of the models that models could have in order to take into account all the BAO data points, including the Lyman alpha anomaly point. And this boils down to that there could be a possibility of negative dark energy density at redshifts, at high redshifts, and that too at Z greater than 2. Now, what are the other hints? So there have been various dark energy models studied by people in literature. I have listed some of them here. Interested one can go and look at the details. So the idea is in all such cases, there is some negative dark energy component at high redshift, and these tend to give a good fit to all the data, trying to simultaneously resolve the cosmological tensions. So now I come to my work. Yeah, the motivation is clear. I want to resolve Hubble tension to construct a dark energy model in the late universe. And I want this dark energy model to have some interesting features like negative dark energy or phantom crossing, which are necessary to simultaneously alleviate the tensions. And I want to motivate everything from a Lagrangian perspective. And for this, I choose to work in the framework of generalized scalar-tensor theory, which is the Horndeski theory. Now, talking a bit about what Horndeski theory is. So it is a generalized, as mentioned, generalized scalar tensor theory in 3+1 dimension, which is constructed from a scalar field and metric tensors, the combination of which always yields second order equation of motion. By choosing appropriate coupling functions, one can have interesting phenomenology to explore different kind of interactions in the Horndeski theory. So this brings me to my particular model. So we are working in a dark energy scenario where there is no cosmological constant. And the Lagrangian for the scalar field is as follows. There is a non-minimal coupling to gravity governed by G4 coupling function. There is a self-interaction kind of term, Galilean kind of term with G3, and there are the usual kinetic and the potential terms. And now the total action would be the sum of the scalar field and the usual matter part. And for the choice of the coupling functions, the G3 and G4 are chosen as shown here on the right-hand side. They are simple monomial function of phi and x being the phi dot square. And one can see that if you just turn off C1, C2, and C3, you just put them to 0, you will just boil down to a simple quintessence type of scenario, which gives similar results as lambda CDM. So it's the C1, C2, and C3 when turned on, it introduces some non-trivial interesting dynamics, which we will see later. So now for such kind of models, the effective energy density of the dark energy field will be something as shown here in the first equation. Here I have segregated the terms arising from the different interactions. So the first two terms are the usual canonical and the potential term, and the terms with the C3 present over here, as you can see that C3 appears in G4 on the right hand side. So these arise due to the non-minimal coupling, NMC I refer to that, and the other last two terms actually arise from the self-interactions part. The interesting thing here is that the third term is with a negative sign, and it does not contain phi dot being very small. So this particular term could really become significant at high redshifts, given that H is high at that H is larger at larger redshifts. And given that we work with positive C3, this could lead the rho phi to get negative in some regime. So this is what we will try to show in our plots. So coming to distinct features of the model. So on the left-hand side, we show the evolution of the Hubble expansion rate as a function of redshift. And here the dashed line is the lambda CDM1 drawn for the reference. Whereas there are other cases, the C1 with the different choices of the coupling function. And we see that there is a lag in the expansion rate at high redshifts in comparison to lambda CDM model, which arises because now we have a negative dark energy density at high redshift in comparison to a constant in comparison to the lambda. And at the low redshifts, there is a faster expansion rate in comparison to ΛCDM, and this arises because of the dynamics of the self interactions, which make the scalar field go into the phantom regime. And this this also ensures that at high redshifts, the expansion rate lagging behind ΛCDM, and at low redshifts, it is boosting in comparison to ΛCDM, that this integral actually remains unchanged, which is a required condition not to disturb the peaks in the CMB. Next, in the right-hand side, I put some BAO data points as well, along with the recent measurement of H0, recent measurement of H0. And we show that due to the negative dark energy density feature, because of which the Hubble expansion lags behind the ΛCDM case at high redshifts, one can actually accommodate the BAO Lyman alpha data points, which were previously not explained by ΛCDM model. And one can also get a large value of H0 at present. So how this looks like in terms of equation of state. So this is the plot for the equation of state for our model. So equation of state is actually non-phantom at high redshifts, and it only becomes phantom at low redshifts, with a singularity appearing because the dark energy density actually was negative at high redshifts, and then it becomes positive later on. So the singularity corresponding to the crossing to the zero, where it switches sign. So, and the present equation of state is indeed phantom, leading to a faster expansion. So in terms of the dark energy density, the profile is as follows. At high redshifts, you can see that the energy density is negative. It is crucial to remember that the total energy density shown here in the subplot is actually always positive. So there are no inconsistencies in the theory. It's just one particular component getting to negative values at high redshifts. Also, at that time, the dark energy was not the dominant component. And also, such kind of dynamics also leads to a phantom crossing behavior, which could be easily understood by a continuity equation. And this type of phantom crossing behavior is something which is required to solve H0 and sigma simultaneously. So because I don't have much of time, I will just go to the that we do some Monte Carlo techniques to sample the parameter space of our model parameters, those being C1, C2, and C3. And we put priors on the absolute magnitude of supernovae as well. And for C3 parameter, which actually corresponds to the non-minimal coupling, we choose negative to positive values to see that whether the data itself prefers C3 to be positive or not, because C3 being positive implies that there should be a negative dark energy. And we use the low redshift data from SHOES, Pantheon, BAO, and the cosmic chronometers. And this is what we obtain the 1 sigma constraints on our parameters to point out that C3 is positive within 1 sigma limits, which indicates that there may be a preference of negative dark energy at high redshifts. We get a value of H0 around 71 from this analysis, which resolves the tension to like 2 sigma, up to 2 sigma with the SHOES measurement. And in future, when we include this whole CMB data, these constraints will tighten. And with this, I will conclude that we try to exploit the phenomenology of the Horndeski models, Horndeski theory, to build up dark energy models, which can have interesting features like negative dark energy density, phantom crossing. And we are working on the full cosmological perturbation theory to in the power spectrum and confront this model with the full CMB data, and also see the implications on the growth tension as well. So yeah, with this, I will thank you all for your patience. And
thank you, Yashi. Thank you for the great talk.